This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
This is Adam Conrad for Software Engineering Radio. EPAN has worked on distributed platforms for internet applications for over 11 years. He started at Yahoo on Yahoo's NoSQL database project, leading the development of multiple features, such as real-time notification of database updates, secondary indexes, and live migration from legacy systems to NoSQL databases. He joined and led the distributed cloud messaging system project later, which is used heavily as a pub sub and transaction log for distributed databases in Yahoo. From 2014, he joined LinkedIn and has quickly become the lead of the Samza team in LinkedIn and a committer and PMC member in Apache Samza. Thanks for coming on to Software Engineering Radio.
Thanks, Adam, for introducing.
All right, so let's get started with Samza.
So Samza actually is a stream processing platform built in LinkedIn. So before we get into the more detailed introduction about the Samza itself, let's first introduce the concept of stream processing. So stream processing data processing in a big data area starts from the MapReduce, Hadoop, and HDFS, which process a large size of the data in batches. The technology is optimized for throughput, not latency. So usually people need to wait for hours or days to get an analytical result from the batch jobs. However, the emerging needs in the dynamic interaction with the user in session for internet applications demands faster iteration and shorter latency in getting the analytical results from the real-time data. This requires us to process the events as they come in and generate results to server online requests in minutes or seconds, which we call stream processing. That's the particular domain that Samza technology is built in, right? So Samza, as one of those stream processing platforms, it started in 2013, late 2013 in LinkedIn, right after Kafka became widely adopted in LinkedIn. The first application that motivated the whole idea is an internal application that tracks the call tree in LinkedIn's microservice stacks. We want to get all the implications of microservices according to a single user request received from the front end, and then being able to join them all together to build a call graph tree to understand, okay, how much time that, how many calls each of the user requests will fan out to, how much time we spend in each of these microservice stacks. From the inception, then, we have built a platform with the following concepts. A, it is tightly integrated with Kafka for high performance. B, it is hosted execution platform to support multi-tenancy. And C, this platform needs to support high throughput and short latency state stores to support stateful stream processing with at least one semantics. So this sounds quite a lot of requirements. To achieve all the above, then Samza actually is designed with the following techniques to address each of them. So we have created an advanced wrapper of the I/O connector on Kafka to achieve per partition flow control when consuming many topic partitions via a single consumer instance. So we were able to achieve using a single consumer instance to consume tens or even hundreds of topic partitions, parallelize processing on all of them, and having a very fine granular flow control for each of the topic partitions. So one of the thread becomes slow for one of the topic partitions will not affect the others. The other, to address to provide a hosted execution platform for multi-tenancy works, we integrate with Yarn as the hosted execution platform to manage the hardware and also the container execution for the user application. That way, then user won't need to manage their own. The user will not need to manage their own hardware. Will not need to manage their own monitor and manage their own process liveness. And Yarn is leveraged as the distributed and hosted execution platform to run these user applications. Third, to achieve the high throughput and short latency for the state stores, we also implement a unique architecture using Kafka as the write-ahead log and then the RocksDB as the local state stores for Samza containers. that allows us to achieve really high throughput and low latency when we read-write the state stores, which is effectively a RocksDB database. So in addition, Samza also leverages Kafka as the intermediate shuffling queues between stages in the stream processing pipeline to achieve the repartition with fault and failure isolation. Lately, we have advanced Samza's APIs a lot as well to add SQL, to add Beam runners and multi-language support on top of Beam, especially Python, to allow easier usage and support richer window semantics via the Beam APIs. So that hopefully gives a overall view of what Samza is, and then how some details about how Samza is implemented.
Yes, that is a very thorough introduction. So I would love to take a higher view. Let's pull it back to maybe a 20,000 foot view. Stream processing in general. What constitutes big data in 2020? Are we talking terabytes of data, petabytes of data? Where does one start when they're looking at stream processing?
So that depends on whether we are looking at the whole collective of all the stream processing pipelines in a company, or we're looking at a single one. As for today, as a whole, we are processing at the north of 3 to 5 million events per second as a whole, collectively in a cluster as a whole. And then in some of the individual jobs, the large jobs can process close to 1 million messages per second, and then having a state store close to 10 terabytes and growing.
And why would I need to process streams of data? What kinds of use cases are people finding for stream processing?
Stream processing usually is, as I explained earlier, that is usually applied to the cases that you want a faster interaction and a shorter latency to get an analytical result. For example, in a session, when user open a website and start to read some articles or click on some interesting content, then those user activities will be sent back in real time to the backend serving system. And usually in the session itself, within seconds or minutes, the platform needs to understand, okay, what is the current user intention, and based on that to supply dynamic contents like further recommendations of more interesting contents or some advertisement pertaining to the user's interest. For example, if the user is looking at some job market stuff, then probably he's interested in a relevant job posting. So these kind of interactions, you cannot suffer from latency that, okay, say, oh, I have this user tracking activities sent back to my Hadoop cluster and wait for 4 hours and get back the result to the user. By that time, the user is already gone.
So anytime I see a recommendation engine where it's recommending me something else to watch or listen to, there's likely stream processing going on underneath to ensure that returns quickly?
Yes, correct.
And so then when should I not consider using a stream processing framework to handle my data?
So stream processing definitely favors latency versus throughput. And because of that, it consumes a lot of resources to store and keep the intermediate result in and the partial and the intermediate result in the system. And it runs 24/7. So if your analytical result does not really impact in-session dynamic engagement with the user, then you can save a lot by doing a batch process, which dynamically allocates tons of resources and then shrink it down and wrap it up once it's done. So that's a trade-off between running a stream process, which is long-running, forever analytical results, analytical flows, versus a batch-based, basically, okay, once the data is there, you can schedule a massive parallelism just to churn through the data all as fast as you can, and then stop, then release all the resources to the system back.
And is there a pivot point where batching just doesn't work and it makes more sense to switch to a stream processing framework? Because I think a lot of companies, batching is definitely one of the first ways that they think about scaling the data that they're ingesting. And so is there a signal that people can look for when they say, okay, batching just isn't working and there's something I might want to consider in advance before they start looking at stream processing frameworks?
So I think there's no like hard set rules for when you should switch to stream processing, but definitely there's some rules, some like because if you start if the batch process you start to have a shorter cadence, then the batch process needs to have a more heavier load on the scheduler, saying instead of every hour you schedule it once, now every hour you need to schedule it 4 times, for example. Like every 15 minutes you need to schedule something. Then it is into the boundary of the area that if that's the case, why don't you just schedule once for 24/7 and then allocate the resources there? Because even in that area, if you're running the 15-minute window batch process, and then each of the batch processing also takes, for example, 40 minutes to finish, then literally you're not saving any resource in terms of like a batch bursting mode that you can use the resource and release anymore, because now you're sort of like continuously using that amount of resource. Then in that sense, then why don't you, the sentiment here is, now with more and more scheduled short latency bursty batch jobs, you actually are continuously using those resources anyways, and you're paying the cost of ramping up and ramping down. Why not just let it run all the time?
Great. And for more information on general streaming architectures, you should check out episode 346, where we go into that in more detail. So that's a good overview in choosing those frameworks. And you did a really great job of explaining Samza at a very high level. So talking more about those internals, I'd like to dive into each of those 3 parts of the core architecture. So we've got the streaming provided by Kafka, we've got the execution provided by Yarn, and the processing itself done by the Samza API. So first, I'd like to start with the streaming from Kafka. So are these 2 projects developed together?
It's very closely. So Samza, as I explained a little bit earlier, Samza started right after Kafka became widely adopted in LinkedIn, and it was developed by even the co-founder of the project is also heavily influenced by Kafka, and even Jay Krabs is also the co-creator of Samza project. So it's literally just a sister team in LinkedIn with Kafka.
And so are they required to work together? Like, do you have to have Kafka in order to be able to use Samza?
Not necessary. So Samza has all this, although Samza is a co-developer, almost a co-developer by Kafka, and leverages a lot of its architecture choices. The implementation leverages Kafka a lot, but all the interfaces are pluggable. So you can, for Samza, you can plug in any systems, PubSub systems, with Samza, as long as you implement the system interface, system producer, system consumer interface, then it will work. Example would be we implemented integration of Samza with Event Hubs and Kinesis. Those are all working.
Okay, so there are examples of swapping out frameworks with Kafka for a different one.
Yes.
Okay, and then is it just the fact that Samza came shortly after Kafka that they said, well, since we have to use streaming as a core service for this group, we might as well leverage Kafka already, since it's part of the same organization and it's already part of the Apache umbrella?
That's definitely one of the aspiration, but at the time that as for a large distributed PubSub system, Kafka at that time is one of those literally just 1 or 2 choices out there for open source.
So right now, Samza is leveraging Kafka externally. It is its own sort of pluggable service, as you mentioned. Is there a plan where Samza can come prepackaged with some dedicated streaming layer as part of the Samza project? Or will it always forever have some sort of plug to a different streaming layer?
The current implementation already have Kinesis and Event Hub implemented and packaged together.
So I guess my question is, those are all external solutions from different companies or different projects.
Right.
Is there an idea to have Kafka be replaced by something that is internal to Samza? So Samza owns the streaming layer.
Got it. So there's no intention to replace Kafka as an internal layer, but we made it architecture to be open. that's the concept.
Okay, so this was a decided choice to ensure maximum pluggability and modularity across multiple systems. Got it. Okay. And then Yarn, a Yarn execution layer, is that meant to stay with just Yarn?
No, there's a definitely extension to that. We spent quite a bit of energy to move from a very tight integration with Yarn, basically Samza cannot run without Yarn, to a mode that Samza can run with Yarn, or you can run a standalone Samza. And we have some experiment. I think in the recent 1 year or two, we already have some experiment deployment with try to run Samza on top of Kubernetes as well, and then that's definitely ongoing. Like we will have integrated with more of advanced state-of-art distributed execution environment.
Okay, now is this the same Yarn I think of? I come from a front-end background. I do a lot of web development. Is this the same Yarn that we use for Yarn package management, or is this a different Yarn system?
Oh, that is Apache Yarn, which is part of the Hadoop ecosystem. It is it's the resource management system that if you submit a job asking for a set of resources to run a set of a process, it identifies the physical host to run the containers for you and manages the liveness of that.
Right. And so in general for folks, this is not the Yarn you're thinking of in the NPM system. This is about, like you said, resource management, job scheduling, job execution. It's ensuring that those jobs that get input through the streaming process data get executed appropriately.
Exactly.
Right. So when I was looking at the architecture, I noticed that Hadoop does many of these same things as well, and it also seems to be the only service that you share. Was this intentional to share Hadoop as that execution service?
Hadoop you mean specifically Yarn, right? So
correct.
Yeah. So just to clarify, Hadoop is a big ecosystem. Yarn is just part of the project doing the resource scheduling, and we only leverage that part. And also, as I explained, Samza leverages Yarn to do the coordination among all the processors in the same job, to have a single master to allocate and assign all the works among all the processes, and then maintain the liveness and the membership of this group. But it's not necessarily the only implementation. The standalone Samza implementation actually replaced that model with Zookeeper-based coordination, which allows a set of processes basically doing the leader election to lead their single leader for the whole quorum, and then do the same like a workload balancing and assignments among all the alive workers, as if in the case that you don't have a Yarn.
Okay, yes, that's what I was going to ask. You mentioned a standalone Samza, so that means just like Kafka, you could also plug in a different job scheduler as well outside of Yarn.
Yes.
So I'm guessing the theme here is that in order to quickly accelerate, and this may just be a guess, but in order to quickly accelerate the development of Samza in the beginning, it was so much easier to leverage Kafka or Yarn because they were already part of the Apache ecosystem than to have to build them out yourself.
Correct. Yeah.
Got it. But the streaming, the actual processing part of the application is done through the Samza API. So I'm guessing when we look at the entire sort of 3-core system, the Samza API itself is the most core and central to this actual Samza app project, right?
Right.
This is the area that has the most unique code compared to the other layers.
Yeah. So one API depends on in my mind, then when we talk about stream processing APIs, in this case, then it will involve not only the I/O wrapper, that I/O connector that read write from the POP subsystem, and also should include the job checkpointing system, the state store system as well. Because in stream processing, without the checkpointing and without the state store management system, you cannot really achieve the failure recovery, and starting from and achieve the at least once and even exact once semantics without checkpointing or state management.
Right. And so when we think about the entire project, this was actually one part that was confusing for me was, what do I actually call Samza? Is Samza the entirety of Kafka plus Yarn and the Samza API, or is Samza just the API part to the whole stream processing architecture?
Samsa actually builds a platform or framework to hide all the system level integrations with with the pops up IO system, with the scheduling system, and with the state source system in a set of APIs going around it, and then allows user to plug in their user logic in the event loop, exposed through this API.
Right. So the stitching layer happens all seamlessly through the API, and then there's a subset of that API that is then revealed to the consumer who actually wants to handle that data and send it through either a container or some sort of job to schedule that for later.
Yes, that's right.
Yep. And so that's actually a good transition point. When I started looking at the Samza API, essentially everything seems to be either a job or some sort of container. So I'm very curious to see how this integrates into databases. So when we think of databases, there are things like ACID guarantees, like atomicity, consistency, isolation, durability. Are there those kinds of guarantees in a system, like in a stream processing framework?
So stream processing, in terms of like at a state, I take it as, okay, if you're comparing the state, kind of a stream processing system with a database, then there's a famous like a stream to table duality blocks that I think a few years ago, JKRAPS posted there, right? So in streaming, then it is always view the table or database as an ever-changing thing, right? And then there's if you're thinking about ACID control, usually it is not in the synchronous. It's not guaranteed in a synchronous way, right? Most of these consistency guarantee is based on the eventual consistency, or you can replay the same sequence and achieve the idempotency as a final result.
Yeah, and actually, you saying that makes a ton of sense. If this data is constantly changing, there would, in essence, there is no sense of consistency ever because it's constantly changing. But like you said, I think the eventual consistency is the right thing there, because at some point, the job will end that you've scheduled, and you're expecting something to look like some kind of result at the end of that job. But while it's processing, it's going to be consistently changing. So that makes sense from a consistency standpoint. Are the jobs themselves atomic? Could you run them again and again and again and expect sort of the action to complete?
Yeah. So atomic is also a strong word that is, I think, only applicable to a single host or single, kind of a CPU and centralized locking system. With stream processing, with Samza as a distributed stream processing platform, like designed from beginning, atomic is not the design principle. The design principle is A, consistency, and also B is the failure recovery with a replayable idempotency. So what the difference is, okay, in atomicity, basically you have few operations, and as you said, you have a job. You want to, the job has 10 different workers, right? And each of them are doing something, and you have to say, okay, all the 10 processes finish one operation in atomicity and then close, synchronize, lock, and then proceed, right? In the eventual, in the way that eventual consistency and the distributed idempotency works is, okay, for each of these 10 processes, you can proceed as your own pace, but you keep the state saying, okay, when you fail or when you shut down the process, saying, okay, oh, I remember process 1 is at step 3, and the process 2 is at step 1. And then you have a vector of all those states of the whole set of processes there. Once you restore the whole process, the checkpoint may always be at step 0 for all the 10 processes. Then when the input are replayed, all these processes will need to check with their own states and say, oh, this step it's already implemented and it's already applied from the previous run for me. I will skip as a no op, and then up to the point that, okay, this is step that I have not executed in the previous run, and I continue, right? So then that's the way that you achieve a replay consistency and idempotency in the distributed system.
Right. Okay. And then, so that really doesn't make sense then to think about it in terms of atomic, because like you said, these aren't short running jobs. These could run for several hours or several days, or just they continuously run. And so
let me just clarify a little bit on that as well. So atomicity, okay, here, if you want to apply atomicity, you can still do that by a centralized logging system. Say you apply a barrier, a centralized barrier through Zookeeper or something like that. But that greatly affects the throughput. And a lot of those stream processing applications does not really work well in the case of you have to keep up with the thousands of or millions of incoming messages as input.
right. So it almost defeats the purpose then. Like you could technically do it. The logging itself almost acts like a ledger then. So you could, like you said, if the service gets interrupted or it goes down for a bit of time, the ledger is acting sort of like the state machine, which says, here's the state at a given time when the service is back up, resume at this line,
correct,
at this given state.
Yeah.
But all that extra logging is going to affect throughput. And so you almost don't, like you're saying, if you needed those kind of requirements for that data, you probably wouldn't even be doing stream processing in the first place.
Yeah, exactly.
Right. That makes sense. Okay. So that covers, I think, the job aspect. For containers, essentially it says that you can execute arbitrary code. So does that mean that security is enforced by the customer, or is it expected by the customer? How does security handle for these containers, which could execute anything?
Right. So that's a good point. So I think for Samza applications, the word arbitrary is also like slightly misleading. So it is just referring to, okay, there's a set of Java API, and then just using this set of system provide APIs, then you can do whatever you want as implementing your user logic. So if the security is in the aspect of, okay, saying, are you able to, in the regular, not really doing any hacky way, are you able to get beneath the API layer to get down to the system level resources and objects, then the security is there, yes. There's no exposure of the underneath system objects to the user. Except for, okay, there's a message comes in, message is there. If you want to use the state store API is there, right? And if you want to input, output, if you want to write to the any system, the producer API is there. That's the level of security that is there. But if you're talking about the user just in their code, arbitrarily write some Java reflection code, try to get some system level instance through reflection. Currently, we don't really enforce that. Serially, in theory, that we can try to enforce this level of security by some access rules or the different class loaders for system versus user space. To enforce that, but that is a good question. We're still working on this, right?
Yes, and it's important to point out too that because you can use Kafka right out of the box, Kafka itself provides no security for those topics. So therefore, by extension, Samza doesn't as well. So what should people be doing to ensure that their streaming code is secure? Do you have any tips or suggestions?
So don't do reflection, right? Don't do reflection, and always going through the Samza system API code to interact with the system, and then including the I/O system, the state stores, and then coordination system, right?
And are there validations within that API themselves, or what kind of guarantees you're saying if the Samza API is the safest way, what kind of guarantees does that API provide that helps to ensure security?
You mean, does the Samza API itself validate whether there's an invalid access to that?
Right. So the APIs themselves have certain type signatures for each function that you're using. I'm assuming that there's security layer baked into all of those functions.
I don't think there is currently.
Got it. And so then what benefit are you drawing from ensuring that you properly use that API then?
So if you properly use this set of API, then the code path is all controlled by the platform. That we actually, as a Samza community member, that we does not really go underneath the skin of certain objects and manipulate with the system unauthorized system objects by default.
Okay, so it's more for debugging, or for, if someone posts a bug to the Apache project, they can say, well, I use XYZ APIs, and then there's some sort of guarantees around trying to fix that, because it's part of you're going through the ecosystem then rather than going around it.
Yeah, because underneath this set of APIs, then no user code. It's all platform code.
Got it. Okay, great. So this is a very helpful introduction to the whole ecosystem for Samza. One really interesting thing I noticed about Apache in general is it seems to own the streaming space overall. And there are a lot of tools for streaming in the Apache ecosystem. So I'd love to take a little bit of a detour and talk more about each of those and see where Samza fits into the overall landscape of streaming.
Sure.
So we've already talked about Kafka. Kafka itself is a streaming framework that you could use on its own. So while Samza allows you to plug into Kafka, you don't necessarily need to plug Samza into, right? So Kafka itself, if you needed to handle streaming of data, you could use that standalone. Spark is another one. What instance would I want to use Spark for?
So if you're talking Spark, so Spark, historically, Spark implements streaming in a micro-batch way, right? So I think only after 2.4 or 2.5, the Spark structured streaming is kind of reinvented the whole API, so that from the API point of view, you don't see the micro-batch anymore, but underneath, there's the execution environment for the Spark structured streaming is still either micro-batch or there's another way called continuous execution, right? And you have to switch between them. The micro-batch is well-adopted Spark way of doing the streaming, and the continuous execution is not yet popular yet, right? And for Kafka, so that's the Spark side thing. So if you compare Samza with Spark, then Samza is a pure streaming engine. So the comparison with the micro-batches, with the pure streaming, you can do event-by-event stream processing and async commit with each of the events, right? And with the micro-batch, you always need to synchronize on the batch boundary, and your checkpoint is also need to synchronize with the batch boundaries, right? So in a lot of use cases, that it's not convenient, right? So that's the short comparison between Samza and the Spark. There, for the comparison between Samza and the Kafka Stream, actually is an interesting story. The Kafka Stream is literally a fork-off from Samza. The reason being, okay, at the early discussion in the Samza community, there are two different schools of thinking that since Kafka is already a popular product, and then there are tons of need that, okay, for small media use cases, I do not really want to stand up my own yarn cluster, my Zookeeper. So I want to have a standalone or as a library, as stream processing as a library as my primary use case. But on the other end, for example, for the logic department like LinkedIn and at that time Netflix and other big installment, having each of the different teams who develop the stream processing pipelines to run their own hardware and having a many repeated SRE and operational effort to monitor those 24/7 jobs across the company is definitely not the way to go. So there's also a strong need to keep the hosted and running stream processing as a service as the primary offering in the Samza community. So that said, not saying that we are not as a Samza community we do not recognize the standalone way of deploying things, just the priority wise. That's different. So literally at that time, then Kafka wants a first party, serving the small media use cases. So they spin off the standalone faster, and it took us some while to get to the dual coordination mode, that implementing the standalone Samza standalone with Zookeeper, but that's the main difference. Like even if you look at a Kafka stream as for today, it is still as a library model. It doesn't really provide, as a service.
Okay, so if I'm understanding you correctly, you'd want to use Kafka Stream for these small to medium instances because it's all baked in together it's just an easier use case. Whereas if you really want to use to the full extent, you'd want to integrate Kafka with Samza. So these larger customers are going to be using the distinct Kafka for its use, Samza for its use between the streaming and the processing portions. But for these smaller use cases, they're going to go with Kafka Stream built into Kafka.
Yeah, I think to me is exchangeable for the smaller media cases between KStream and a Samza standalone is kind of exchangeable. Kafka Stream may have a little bit lighter weighted in terms of Zookeeper setup and those things. Yeah,
got it. But LinkedIn themselves is using the full
LinkedIn
Kafka.
Use both actually.
Oh, you use both.
Yeah.
And what instances internally are you using KStream for versus?
No, not KStream. LinkedIn use both Samza's Yarn and standalone. Right. Yeah.
Right. Got it. Okay, that makes sense. So there's way more than just those two. So we've covered Spark, which is definitely more in the sort of cluster computing, big data analytics. We've got KStream, which is another sort of standalone service that's more integrated into Kafka. And it sounds like Spark then, just to wrapping up that piece, Spark is probably used before you would want to use something like Samza, given you're using batching is definitely something you're going to be trying out before you're trying out a processing framework. So do you find a lot of people coming from Spark and then trying out Samza, or is it just different use cases in general?
So in early days, Spark is and the Samza, Spark and the Stream side is kind of a mostly isolated silos, and people who want to write batch jobs use Spark, and then people who want to use the real-time analytics write in Samza, right? But we've seen as like since 2016 or 17, we've seen more and more use cases wants to do both, right? And that's exactly also our journey toward try to get a convergence API between the batch world and then the stream world. And so far, our strategy is we actually discovered in the year of 2016 and the later 2017, Beam is a good choice for us, because Beam API is stressing for basically putting a lot of rich stream processing semantics and syntax on the API, but the whole API layer is engine agnostic. So the Beam's architecture is there's an API layer describing all the user logic, what you want to do with a stream processing. But underneath, you can have different runners, which is a damped layer to translate user logic to a particular engine. For example, Spark can be an engine there, Samza can be an engine there, Flink can be an engine there, and even there are more like Apex and others, right? So we feel that is a best fit for our strategy, because if you compare the different different engines in LinkedIn, that Spark has tons of optimization for throughput and integrated well with the batch ecosystem. Stream side, Samza has its own tons of optimization in the runtime and integration with the nearline and online ecosystem in LinkedIn. So there's a huge gap if you want to replace one versus the other. Yet you probably need to spend years of effort to replicate the optimizations you've done on the other side. But with Beam, since the Beam application Beam layer allows the user to just focusing on the application logic, then the optimization and also how do you run the same logic on stream versus batch environments becomes kind of a hidden layer from the user, right? So that allow us to have kind of a more quicker integration for the convergence use cases, and allows to advance on the optimizations for each different engines separately.
And this Beam layer you're talking about, is this the same one that powers Erlang and Elixir, the concurrency languages?
No, the Beam is Apache Beam, which is, I think, is a project started in 2016, and right now it becomes the top level Apache project already.
Yeah, there are just, the more I sort of unpacking this, the more you can see that Apache really has so many services that power this whole streaming space. And you also mentioned Flink earlier, which is more for distributed data flow or parallelization. So that sounds like it's another system, yet again, where it's not about necessarily replacing one thing with the other, but it's about complementing each other through this Beam layer.
That's the thing that if I want to say a short comparison with with the landscape, I usually categorize in 4 different aspects, right? So talking about all the different state-of-art platforms and engines out there. One aspect is whether the API is pure streaming versus microbatch. So you can see that Flink and Samza actually is mostly pure streaming because usually the API is event-by-event processing, allows async commit features and those things. And Dataflow, which Google Dataflow and the Spark structured streaming mostly operate on the microbatch mode. But then that's the API layer of difference. The implementation architectural layer of difference is, okay, there are RPC versus shuffling queues in the whole pipeline. So that's if you compare all the different systems, it's very unique. Like for Samza, Flink, Dataflow, and Spark structured streaming in a single job pipeline, they all use RPC between the stages of a single pipeline, which has to be started on timeout when the communication between the operators in different stages have issues, right? From the upstream, downstream. Samza, implements a different way that it leverages the Kafka queue as an intermediate shuffling queue. So instead of RPC. So if you have intermediate, stage 1 produce something, stage 2 continue process this output from the stage 1, it is all communicated through a Kafka queue. So it has advantages of, okay, you isolate the failures in the downstream from the upstream, and you guarantee the orders of all the sequences that once you materialize once of all the events you want to process, the downstream will all see the same sequence there. The downside, of course, is added some latency and also added some persistent cost in the whole pipeline. Right. That's the second aspect. The third aspect is, okay, the large state store supports. So if you compare all these, then Flink and Samza actually comes with very comparable feature sets that it all comes with the native free offering of RocksDB-based local store for large states. Spark structured streaming by default offers, okay, HDFS-based state store. If you write a map with a state operator in Spark, right? The issue is that as quoted from Databricks offering on Azure, the free state store implementation on HDFS has some performance issues when the size of each state goes beyond a certain size. I forgot exact number, but I think it's in the gigabyte range. Then in that case, you will have to purchase the RocksDB-based state store for the largest state store from Databricks as a proprietary offering, right? So that's a difference, right? Okay, the whether for Flink and for Samza, that by free you get the state store of the largest state store support with the RocksDB, and in Spark you need to pay money. Right? And then last aspect I was thinking is to compare all those is a cloud integration, right? Whether you have a native integration with the public vendor as a service. So on that front, actually, Cloud Dataflow and the Spark streaming has a better integration, as they all, Cloud Dataflow is a native offering from Google. Spark streaming has the offering, basically the first-class service offering from Azure. Flink and Samza mostly are freelancers, so you can just run your own cluster, run your own service by yourself. But as for now, there's no cloud vendor-based offering for that yet. hopefully that's giving a overall comparison that I have. Right?
Yeah, and there's yet another project that I think stitches some of them together. One of the topics you mentioned that's a big differentiator between the different services is whether you're focusing on batching versus pure streaming. Apache Apex is yet another streaming tool that's mostly around processing either streams or batches. So it sounds like if you'd mentioned this earlier with Kafka, that if you have Spark, you could complement Spark with Samza while one handles the micro batching and one handles the streaming. It sounds like Apex could be that meta processor that's allowing either streams or batches to complete like through this system. How would you use Apex in that sense?
So Apex itself is an engine. So I don't think Apex itself is an API layer. What I was mentioning earlier is Apache Beam is an API layer. So it doesn't really demand a specific engine to run beneath. And Apex, I think, it has a Beam runner. Basically, it runs the Beam program as an engine, but itself is not. It is designed as a convergence engine, but I don't think itself you can swap in any engines beneath that.
Okay. Yes. So in that sense, if you didn't want to use Beam, Apex could run the whole thing for you because it is itself the engine that's powering this.
Yeah, you can choose to all in for Apex, but unfortunately, I don't think the project is currently very active, and it also comes way later than what we have demand on and we have developed.
Got it. Okay, and then to sort of rounding the quarter here in Apache streaming projects, the one that actually sounded most similar to me, you had mentioned that there's a lot of similarity in pure streaming between Flink and Samza, but I also noticed Storm sounded very similar as well too, because that handles stream processing computation. So I'd imagine that there's a lot of overlap with how
Correct.
Samza processes the jobs or the containers that are in those jobs, right? So it sounds like you might actually have to look at the comparisons.
Storm was an earlier competitor with Samza that we analyzed. I think there are a few disadvantages we see in Storm that at the moment stop us from investigating that. One is Storm's large topology management, like the Nimbus-based large topology management, is not quite reliable at the time. That often causes stalling of the pipelines. And then the other is, Storm doesn't really come with a good large state store support with short latencies, right? So even for that effect, for that aspect, in fact, Samza was the first one integrated with the RocksDB by native first class support. Flink actually works with the in-memory state store offering first. Then it comes with a for log with a RocksDB implementation. Storm doesn't really have that at the moment.
Okay, so at this point then, Storm is not something that people are actually actively trying to compare. Like if you're going to choose something in the computation space, you're going to be choosing Samza. You're not going to have to worry about Storm at this point anymore.
Yeah. So for us, I think in my opinion, the most currently, if I'm looking at what are the top competitors in this space, I'm going to be looking at Flink and then Spark Structured Streaming. Flink is, in a lot of sense, that functional-wise, offered feature-wise, is very close to what Samza is offering. Spark Structured Streaming, the main reason is Spark has a big ecosystem from the batch side, right?
So then how do I know which framework to choose? If there's so many to evaluate, what am I actually looking for in particular pieces to help me choose the right system for me?
Right. So that's from our point of view, then we always stress for performance, right? So I cannot really, I think it's hard to come up with a general rules or reasons for people who want to choose A versus B. I can explain several reasons why Samza is adopted as a mainstream processing engine in LinkedIn, right? So from the LinkedIn perspective point of view. So the first reason is performance. So Samza's Kafka interface is thus far the most advanced I/O connector on Kafka among all the stream processing platforms that I'm seeing. if you look at most of the stream processing platforms, integration with Kafka is saying, okay, each topic or each topic partition, you have to have a consumer instance for that, right? So then this Kafka instance will feed for a task in a task for processing this in order sequence coming from a partition. But then if you're consuming from many different topic partitions, one disadvantage we've seen is some of the platforms that basically need to instantiate multiple Kafka consumer instances in the same container to consume multiple different Kafka topics and topic partitions from that. And in order to having a one-to-one mapping from, okay, there's one input sequence, there's one thread processing that. It works with two conditions: A, if the input topic partition is relatively static set, and B, the number of total memory footprint of all this number of topic partitions, including all those number of consumer instances in a single process, is not a high pressure. But Samza works in a more advanced way that we actually instantiate a single consumer instance for the Kafka cluster. Even you're consuming from 10 or even 100 of the topic partitions from this cluster. And then internally, there's a multiplexer and also a per partition flow control mechanism that we see, okay, this multiplexer will take the messages from all the topic partitions, fan out to different thread that is working on different partitions. And if one of the thread is going slow, we just pause on this particular input partition, which doesn't really pause the whole consumer instance. A lot of other systems will do, right? So that allows us to shrink, doing a very dense consumption model in a single consumer instance, yet to maintain a high throughput in terms of, it needs to fan out to multiple parallelism. That gives a lot of benefit in terms of like performance for Samza processing. The other advantage, of course, the integration with native integration with RocksDB as a local embedded store, and which it yields the sub-milliseconds read-write latency and a strong synchronized read after write semantic consistency in the state store read-write. We had an earlier performance benchmark show that Samza supports 1.2 million requests per second on a single host in a very old host with only like a 1 gig NIC, right? We have no reason to not believe in that it can scale up with the modern hardwares with 10 gig NICs and other beefier CPU and memory. That's the one big aspect of LinkedIn choosing Samza, right? There are also LinkedIn's reason for choosing Samza also is, okay, with the improved APIs with rich windowing semantics. So that is coming from two aspects in terms of the API improvements since 2016. We started supporting SQL. So SQL supports allows many users, such as data scientists or AI engineers, to write the stream processing pipeline without understanding underneath system details. And B is we are integrated with Beam APIs. Samza Beam Runner is the one that we built since 2016, which allows us to leverage the rich semantics of Beam APIs, specifically windowing and event time. And also there's triggers, which is a very advanced API and concepts in the stream processing. You can read Taylor Akido's Stream Processing 101, Stream Processing 102 to understand what is a trigger and late arrival and early arrival means, right? This also allows us to support multi-language support from Beam, which recently we have successfully advanced to support Python stream processing applications in LinkedIn, right? So that's the API side. And those are all built on top of a high-level API in Samza, which allows you to specify the multi-stage pipelines in a single application executing there's much of a work that is still going on with SQL and Beam. The third aspect that I want to mention is we have actually improved on the operability at a scale for stream processing on Samza quite a bit. So the biggest challenge, of course, in stream processing is maintaining a large number of stream processing pipelines with strict SLAs 24/7. We have actually put a lot of effort into, in many aspects for that. I will only mention two here. One is we actually added advanced auto-scaling capabilities in Samza platform. One of the biggest complaints, of course, from users is, the complexity, difficulty in tuning the configuration of a running pipeline. The incoming traffic fluctuates, and when you deploy the same pipeline from data center A to data center B, the traffic difference, and then the hardware may be different. So there's tons of the tuning you have done in data center A doesn't work for data center B. This is a nuance, and creates a lot of pains from the user. This is especially true for SQL users, since SQL users mostly are not familiar with the operational details of physical system. So SYNC has put a lot of effort in providing tools and systems to help monitoring and auto-scale the jobs, so our users won't need to carry the operational overhead. Our recent success in this effort, you can find it in a paper in Hot Cow 20. The title is Auto-Scaling for Stream Processing Application at LinkedIn. We actually deployed the auto-scaling system together with our largest scale operation of the Samza pipeline in LinkedIn, and achieved great performance and also operational cost savings. And we view it as an important differentiator of our technology. The second aspect I want to mention in this operability improvement is the large state failure recovery and resilience. So as I explained earlier, Samza leverages RocksDB for local states, and Flink follows, and even Spark structured streaming when you need to have a large state. It also provides the RocksDB as the local storage. It provides the fast access to the in the healthy state of the job. But Samza uses Kafka topic as a changelog to recover the state stored in failure, and this is heavily tuned toward the healthy high throughput in runtime, but the recovery from the Kafka topic is relatively slow. So we actually implemented two solutions to fasten the state recovery already. One is host affinity in Yarn. So we allow the job to schedule the container back to the same host in Yarn if the host is still available. Then we can leverage whatever the local snapshot that exists on the Yarn host and fasten the recovery. This actually in production achieves 50 times or 20 times faster recovery. And the other is to battle against the case that the host is totally gone. So it's called hot standby container. We have implemented a way that you can stand up hot standby container in another host, which keeps the state in sync and immediately take over the work from the failed container if the mission is critical. That is allowing us to operate in the range that for mission critical jobs that you cannot really suffer any downtime. There are works still in progress to improve the state recovery in case of host failures going on. Try to strike a balance between the cost you pay in having many standby hosts, standby containers, versus the time you take to recover. So that's the third aspect of that. And just want to this is a set of reasons that we choose Samza as the runtime platform in LinkedIn. Right? There are examples of the Samza users like eBay, Redfin, TripAdvisor, Optimizely, which is a market analysis company, Slack, and those companies all think most of their use cases chooses Samza because of the above reason.
Great, and we'll link to all this documentation on the show notes, so you'll be able to see the Samza official website, the Twitter, the link to other resources at Awesome Streaming, as well as the paper you referenced earlier, Auto Scaling for Stream Processing at LinkedIn. So we're basically going to wrap things up. Could you just summarize really quick, when someone's ready to make the dive into Samza, what kind of things, what sort of parting advice could you give to folks if they're looking to get started with streaming, stream processing, or Samza in general?
So I think, first of all, so when you're looking into a stream processing platform, of course, I think you will need to understand, in this domain, the throughput, fast performance, and consistency is a big trade-off. So just keep in mind that in any distributed streaming platform that you may need to pay, you need to look for those trade-offs between that. And if you're specifically looking for a comparison between the stream processing platforms, I think, as I mentioned earlier, then API, the four aspects I will recommend is, look at API, see whether it's pure streaming or micro batch, and look back to your use case, whether you can take the micro batch way of writing your logic, or you have to do a pure stream way, because there's some logic that is hard to align the logic with the batch boundary. For example, the session windows and other things, right? And then the other is about the other aspect is, for the whole pipeline, that how much of a consistency regarding to atomicity, or not atomicity, but most of the consistent snapshot or exact ones you want to achieve. If you want a strong exact ones across the whole pipeline, then you may pay the additional cost of synchronization of the states in different stages, which RPC is probably give you a better option here. But if you are going with, I do not want to sacrifice my performance because of that, I want to have a eventual consistent way, and being able to isolate different stage of failures without impacting other, then a persistent shuffling queue may help to solve your problem in between the stages of a pipeline. The size of a state store is another big problem if you're doing a stateful stream processing. Then I would recommend that if the size is big, then look for a RocksDB solution. Yeah, mostly is that. And lastly, on the cloud vendor integration side, then it is up to your appetite of, do you want to have your own installation and have to run a stream processing cluster, or you can leverage some existing cloud vendor offerings. That's just a start with. There are a lot more details to evaluate.
Perfect. Well, we're just about out of time. Thank you so much for coming on Software Engineering Radio today.
No problem. Thank you a lot, Adam.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website, or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.